Yeah, you can start now.
Good evening, everyone. It's my great pleasure to introduce today's speaker for the Special Functions and Number Theory seminar, Dr. Rahul Kumar from Penn State. So Rahul did his PhD under my supervision, or I would say I was fortunate to advise him for his PhD thesis at IIT Gandhinagar. He completed his degree in 2020, following which he had a brief postdoc position here and then at Institute for Basic Science in South Korea. Now he's a Fulbright Nehru postdoctoral fellow at Penn State. He'll be talking today on his joint work with Professor Young-Ji Choi on Herglotz-Zagier-Novikov function. Yes.
Thank you very much for kind introduction, sir. So, good morning from me to everyone, and good evening for you in India. So, today I will be speaking on this topic, arithmetic properties of the Herglotz-Zagier-Novikov function. So, this is joint work with Professor Young-Ji Choi. So, here is one photograph of her. So, this talk will be based on this paper that we submitted recently for the publication. So, this is the outline of my talk. So first we will discuss some basic definitions for Riemann zeta function and some of its generalizations. And then we will discuss what is Kronecker limit formula and what is its history. And then we will be discussing some functions that appear in these kind of Kronecker limit formulas. And then I will discuss our work in this area. Okay, so let's start with this basic definite integral. So you can see this is it is an definite integral which contains only elementary function in its integrand. So you have this log and this polynomial in the denominator. So when one sees this integral for the first time, one may think that it may be like easy to evaluate this integral for some special values, like for natural numbers of x, or like for rational numbers or quadratic units or whatever. But it turns out that it is not easy actually, and that's why maybe Chawla in one of his paper mentioned that a direct evaluation of this definite integral is probably difficult. And we will see in upcoming slides that is the case, that all of the evaluation of this integral actually comes from like various non-trivial techniques coming from algebraic number theory or analytic number theory. So now let me start actually the talk. So let me start with the basic definitions. So we know that Riemann zeta function is defined by this Dirichlet series is in the right half plane, real part of is greater than 1, where this series is uniformly and absolutely convergent and defines an analytic function as well. Not only that, it can be analytically continued to the entire complex plane except for a simple pole at s equal to 1. So for pole at s equal to 1, one can evaluate the Laurent series expansion for this Riemann zeta function, which is given by this following formula. So you can see here you have this pole and residue is 1 only. And then you have this constant term minus gamma, which is nothing but Euler's constant. And then you have this higher order Laurent series terms in here. So our interest in this talk will be this constant term in various Laurent series expansions. So just focus on the what is constant coefficient in this Laurent series expansion. So here it is minus gamma. So now for the record, just let me also mention Hurwitz zeta function, so which is also defined in similar fashion as Riemann zeta function. Now you just have this translation by A, and it can be also analytically continued to the entire complex plane, and it has pole at s equal to 1, and the Laurent series expansion can be given by this formula. You fix A between 0 and less than equal to 1, then your Hurwitz zeta function has this formula 1 over s minus 1 plus psi of A, and then again these are the higher order terms. So here this constant coefficient is just psi of A, which is nothing but logarithm derivative of the gamma function, which is commonly known as digamma function. And when you take A equal to 1, it actually reduces to that Euler's constant. Okay, so these Riemann zeta function and Hurwitz zeta function are functions which are like defined for rational number field, right? So what about the number fields? So for every number field, we know that we can attach a zeta function, which is known as Dedekind zeta function. And it can be defined in this fashion, where you have 1 over n raised to the power s, and your now sum runs over all integral ideals of OK. and n of A is nothing but the norm of ideal A. And this Dedekind zeta function can be dissected in terms of that class number, and that sum now runs over the ideal class group of K, and this partial zeta function can be defined in the similar way as Dedekind zeta function, but now that ideals are coming from that ideal class group on ideal class only, ideal class A. Okay, so question is, what is the Laurent series expansion for Dedekind zeta function? So generally you can write in this form for any ideal class A. So important thing that we know that what is the residue of this zeta function at s equal to 1, and one important thing that residue doesn't depend on A, it is independent of A, and this constant coefficient does depend on A, so we denote it by rho of A, and then you have these higher order terms. So question is that what is this rho of A? What is the expression for this rho of A? So that is not known for general number field, and that is what is known as Kronecker limit formula. So we are interested in evaluating this rho of A. It was like kind of easy for the Riemann zeta function and Hurwitz zeta function, but it's not easy for the Dedekind zeta function, and that's why it has a special name, and it will be clear why we are calling it Kronecker limit formula from the next slide. So actually we are interested in this limit, right? So limit s tends to 1, zeta sa minus that kappa upon s minus 1. Okay, so what is the then Kronecker limit formula for Riemann zeta function? We know by our discussion that is minus gamma only. And what is for Hurwitz zeta function? It is psi of A only, right? So now we are interested for the Kronecker limit formula for Dedekind zeta function. So this problem started with the Kronecker, who accomplished this formula for imaginary quadratic field in 1863. So that's why this problem now known as Kronecker limit formula, because he was the first person to evaluate this for any number field, like at least for imaginary quadratic field. And then later on, Hecke obtained this corresponding formula for real quadratic field, but his formula was not explicit. We will see his formula and we'll discuss why we are saying that his formula is not explicit, because later on in 1975, Zagier actually found out one nice formula for Kronecker limit formula, which contains some universal functions. It doesn't contain like some complicated expressions. So this is the little bit history of this problem. So now let me show you what is the formula for of Kronecker for imaginary quadratic fields. So you take this positive definite quadratic form, and then you take W be the solutions of this quadratic equation, so that you can write this quadratic form in terms of this expression mw plus n, that modulus whole square and divided by imaginary part of W. Then the zeta function, it can be proved that it can be extended meromorphically to a neighborhood of s equal to 1, where it has this following Laurent series expansion. You have this residue 2 pi, and then this constant term C can be evaluated in this form, where you have this log of eta coming up, which is Dedekind zeta function. So suddenly one may think like suddenly why we are talking about these kind of zeta function instead of Dedekind zeta function. So for that, let me just say briefly that that Dedekind zeta function over imaginary quadratic field can be like actually translated to this zeta function only. And for that, what we do, we just fix an ideal in this ideal class A inverse, and this map A going to AB actually gives you a bijection between set of ideals of that ideal class A and the principal ideals, which are divisible by that your fixed ideal B bar, that B. Okay, and then we know that any two numbers define same principal ideals if they are like a product of each other up to some unit of that okay, that is a ring of integers, right? And then that means they have to be in this set. So OK star denotes here the group of units of ring of integers. Okay, so this is the definition of that partial zeta function, right? What we have done, we have just multiplied by this quantity and divided by the same quantity. Now you can write this AB in terms of this lambda, right? Because we have shown that this is a bijection actually. Okay, so you have L lambda raised to power S. So now if our field is imaginary quadratic field, so we know that this okay, that group of units actually is finite for imaginary quadratic fields. So you can write this last this step, because this is the like a cardinality of that okay star, that group of units. So for imaginary quadratic field, that group is finite. So we can write this last step. So now that problem now boils down to this expression, that some infinite term on the right hand side. So now what we can do, we can take a basis for that your fixed ideal B, like 1 comma W, and then your lambda can be written as this in form of that basis MW plus N, and then you can evaluate that norm like this MW plus N, that modulus whole square. So you can now write this partial zeta function in this zeta function. And from here, actually, that Kronecker evaluated that Kronecker limit formula that we have seen on the previous slide. Okay.
Rahul, can I ask one question?
Yeah.
So here, are you assuming that this imaginary quadratic field is principal? Like, okay, so here A times B bar, you are writing it is like principal generated by some lambda.
Yeah. Because,
So
because this is a class group, right? This A is coming from the class group, and the identity element of that is that ring of integers, right?
okay.
So all the ideals, when you multiply, this A is coming from A. This A is coming from the ideal class A, capital A, actually. So when you multiply that with its inverse class, so it will be naturally it will be a principal ideal.
Okay, I see.
So yeah, so that's why it is a bijection between principal ideals divisible by that your fixed ideal B and set of ideals coming from A.
Okay, I see.
Yeah.
Okay, thank you.
Yeah. So important thing is that on this last step, you can do for only imaginary quadratic field. We cannot do it for real quadratic field, because in real quadratic fields, that group of units is infinite. So you cannot write this that divided by this cardinality of OK star. So it is valid for only imaginary quadratic fields, not on any other number of field. So that's why that problem was there. So one couldn't do it for real quadratic fields. It was only possible for imaginary quadratic fields. So then later on, Hecka actually solved that problem and find out the following formula. So here you can see in his formula, you have this integral containing this log of eta. And this integral is running from minus log epsilon to log epsilon. And this epsilon is fundamental unit of that real quadratic field. So you can see that this formula is not explicit because it has that integral, and inside that integral, you have this log of eta appearing. So that's why we said that it's not an explicit formula, because we will now see the formula of Zagier, which is more fundamental and more like a more beautiful formula for this rho of A. So this is the formula of Zagier. So now you take this quadratic form, which is indefinite quadratic form, because now we are taking discriminant is equal to 1, and then you take the solutions of this quadratic equation, so that you can write your that quadratic form in this form, and this W is just algebraic conjugate of W, and then there this zeta function, which is similar to kind of in the case of imaginary quadratic field, but difference is that now your sum runs over only the positive, like rational positive natural numbers instead of whole integers Z. And then you can prove that this zeta function is actually analytic in right half plane, real part of is equal to half, and then can find the Laurent expansion at s equal to 1, where this PWW prime function can be given by the following expression, where you have this f of x minus f of y, and this dilogarithm function, and some elementary functions log and all. And so let me define this Li2, which is known as dilogarithm function. And more generally, it can be defined in terms of polylogarithm function. So these LIS function is actually a generalization of log natural logarithm function. That's why it is known as polylogarithm function. It has analytic continuation both variables in S and T. It's a well-studied function in the literature. And this f of x function actually is known as Herglotz function, and which can be defined in this following infinite series, where you have psi of nx minus log nx over n. and your x can be in this silted complex plane. And this silted complex plane, this Herglotz function is actually an analytic function, is a well-defined function and analytic also. This function named after the name of mathematician Herglotz. It was named Herglotz function by Radchenko and Zagier in their recent paper, but later on some authors call it Herglotz-Zagier function, because Zagier was the person who actually realizes the importance of this function. So we will discuss in coming slides. So we have seen up to now we have seen the Kronecker limit formula. So this problem is interesting in itself, but not only that, it has many non-trivial applications as well. So now let me discuss one or two non-trivial applications of Kronecker limit formula, and then later on we will proceed further. So you define this L function for ideal class characters, and then you can rewrite this infinite term in terms of this partial zeta function. And s tends to 1, we have seen that what is the Laurent expansion in general for any number field. It is like this as s tends to 1. And as I have mentioned earlier, that this kappa is independent of that ideal class A. So that first term will vanish because that is independent of A, and then you are running that sum over all the ideal classes. So that first term will vanish. So we are just have now this finite sum chi of A and rho of A, and then this big O of s minus 1. And then you take s equal to 1. So your LK1 chi is nothing but this finite sum chi of A and rho of A. All of the terms will be gone, right? So if you want to evaluate this L function at s equal to 1, we have to have this Kronecker limit formula. So that evaluating that L function at s equal to 1 actually reduces to finding a closed form expression for Kronecker limit formula. And why this L1 chi is important? Because it is related to class number. So why this is related to class number? Because we have seen this expression, and this is the Laurent expansion of zeta of SA. If you take this limit after multiplying by s minus 1 with Dedekind zeta function, actually in this first expression, then using this Laurent expansion, you can see that these terms will be gone after taking limit. So you are just have now this summation running over all the ideal classes into kappa, and kappa is independent of A. And so what is that? That is kappa into h. H is the class number. So these are the s is the number of ideal classes in that class group. So h denotes here class number. Okay, so now from here we have this expression. On the other hand, for any quadratic number field, you can write your Dedekind zeta function as a product of Riemann zeta function and this quadratic L function. So now if you take this limit, multiply s minus 1, and then you take limit s tends to 1 on the both sides. So s minus 1 zeta s gives you 1, right? Because residue of the Riemann zeta function is 1. And what you get L1 chi on the right hand side. So from here and from first equation and the second equation, what you get is L1 chi equal to chi into h. And from the previous slide, we know that L1 chi is in terms of Kronecker limit formula. So you have now relation between class number and Kronecker limit formula. So that means finding a closed form expression for class number actually gives you a better understanding for class number. So that's why this whole interest in finding Kronecker limit formula is due to this problem also. So there are various applications. Kronecker himself actually provided solution to Pell's equation, which is nothing but kind of construction of a fundamental unit for a real quadratic field. So one can look at the lecture notes of Ziegel for a nice explanation of Kronecker limit formulas in analytic number theory and algebraic number theory. And there are many other papers also. So one can look at this paper of Ramachandra, where he actually gave various applications of Kronecker limit formulas of Kronecker or Hecke, and there are like various applications. Okay, so now let me come back to the functions that appear in Kronecker limit formulas. So we have seen that Herglotz function appeared in the Kronecker limit formula obtained by Zagier. So recently, Radchenko and Zagier wrote this paper where they studied various properties of Herglotz function, where they find out the various functional equations satisfied by f of x coming from Hecke operators. They evaluated it for like a positive rationals, quadratic units. So there, this is a like a nice paper. Okay, so most important property of Herglotz function is that this function actually satisfies two beautiful functional equations known as two-term functional equation and three-term functional equation. So these functional equations were provided by Zagier in his 1975 paper only. So these kind of functional equation are known as two-term functional equation, where on the left-hand side you have this function f, which is Herglotz function at two different argument at x and 1 over x. It's kind of giving you a symmetry for Herglotz function at x and at 1 over x. And then you have this three-term functional equation, where you on the left-hand side you have now function f at three different argument at x, x plus 1, and x over x plus 1. And on the right-hand side you have again some elementary functions coming up. So these
here, what is x? X is just real part of x is greater than 0, or
no, x can be in the selected complex plane.
okay, okay.
Yeah. So yeah, so these are the like a two-term and three-term functional equation for f, and they have various applications. Zagier have given in his paper. One can look at his paper, 1975 paper, for some of it their applications. An important thing that these three-term functional equation appear in various areas of mathematics, such as period function for mass form, cotangent function, double zeta function. So this is a paper of Zagier in French. So one can look at this paper where he mentioned various areas of mathematics where actually these three-term functional equations appear. So for example, period function, we know that are solutions of this three-term functional equation. And in the same paper, Zagier actually remarked this in French. So I used Google Translator to translate this remark. And what it says that if ever during your mathematical studies, you discover in nature, of course, in mathematical nature, that's the only one that's true. Anything where there is an x plus 1, and x plus 1 over x, you send me a little email and I will try to do it fit into the journal scheme. So this remark itself kind of tells us the importance of three-term functional equation in mathematics. So I would request all of you, if you find any three-term functional equation, you can contact Zagier, and then you have better chances to get a reply from him. Otherwise, it is difficult. So let me go now. Let me like study or like discuss some of other properties of these Herglotz function. So this f function is defined by this infinite sum that we have already seen, and it can be written in this integral form like following. So you have this just elementary function in its integrand. So there are many other functions also that appear in various canonical limit formula. So I will mention some of them here, which are interested to our discussion. So this function f actually appeared in the paper of Herglotz and Zagier. Herglotz paper 1923 and Zagier's paper 1975. Then this j of x function that I mentioned on my first slide, it appears in the paper of Herglotz in 1923. And Muzaffar and Williams in 2002, they studied a canonical limit formula for a restricted Epstein zeta function. And in their canonical limit formula, actually these three functions, all f, j, and t appears like together in their formula. So these are some functions that appear. And in 1981, Novikov written this paper, and where he actually stumbled upon this function where you have this log 1 minus ut raised to power x divided by v inverse minus t. And you have this real part of x greater than 0 for the convergence of this integral. And then you have to take this u in any complex number, but you have to remove that line, real line starting from 1 to infinity, because otherwise this log function will have branch and all. So to avoid that branch, we have to remove these values of u. And to avoid the principal value integral, we have to remove these values of v from the complex plane. Starting from, you have to now remove 1 also. So this is the function of Novikov. So these are the three functions that I mentioned on the previous slide. So let's discuss the what can be like their relation between these functions. So if you want to take v equal to 1 in this script f function, so you will have in the denominator 1 minus t, right? And then this integral will diverge at t equal to 1. So for that, to convert to like have a well-defined function, you have to add and subtract this term 1 over log t. So that means this Novikov's function is actually kind of extension of this Herglotz function. So you take v tends to 1 and just add and subtract some terms, then you may get this Herglotz function. And what if you can take u equal to -1 and v equal to -1? So this will be plus sign, and here minus, and you take that minus sign out. That means this script f function is a generalization of this g of x function. And first, when we look at for the first time, it look like that this script f function and t does not have any relation, but they do have a relation. I will mention that. So this function f actually kind of combining all these functions together in one function. So we named this function as Herglotz-Zagier-Novikov function. It is a long name, but we have to do it because now this function known as Herglotz-Zagier function in the literature. So, and it when we studied this function, it has very nice property that I will discuss in coming slides. So we decided let's include the name of Novikov also in the name of the function. So it is now we have like named it Herglotz-Zagier-Novikov function. Okay. So this is the relation between J and F, which was provided by Radchenko and Zagier in their paper. You can see on the right hand side, you have three F Herglotz function at different arguments. And I have just mentioned it that when you take u equal to -1, v equal to -1, that script f function just reduces to g of x. And when you like do that addition and subtraction to take that limit u tends to 1 and v tends to 1, it actually reduces to Herglotz function, this script f function. And then between t and f, that t that I just mentioned here, that has an arctan function in this. So this script f function and t does also have a relation. You have to take this linear combination of f at 4 different arguments. Then you can take you can get this t also from f. And there is a relation between t, j, and f. If you take this combination, you just get 0 on the right hand side. So these are some relation between of f with these functions j and t. So it looks like that if we develop the theory of this script f function, it will also develop the theory of j and this t function and that Herglotz function. And the j function has been studied by many mathematicians. I will name some of them. And t function also only studied by Cohen and Muzaffar and Williams. So if we study this script f function, it will like give us some properties for these functions j, t, and f also. So now let me define these sets. You take this D set, which is unit disk, including its boundary, but you have to remove that 0. So it's like a punctured unit disk, this D set. And this D prime is, we have to remove that 1 also from that punctured disk. And this D1 is nothing but just unit circle. And D1 prime is, you are removing that 1 from the unit circle. We are removing 1 because, as you remember, that we cannot take v equal to 1 in our script f function. That's why we are removing that 1 from everywhere. And 0 for the obvious reasons, because 1 over v will not be defined. Okay. So this function f has these 2 simple formulas. It is not difficult to prove them. They are like a kind of doubling formula that u square is going to u and minus u, and v square is going to v and minus v. So these are some simple formula that actually help us to study some of properties. So most important properties are, the first question was, does this function satisfy 2-term and 3-term function equation? Because it has 2 parameters in comparison to Herglotz function. Herglotz function has just x, but now it has u and v also. So you have like 3 parameters. So can you get 2-term and 3-term? So it is possible to get 2-term and 3-term. So this is the 2-term functional equation where you have x and 1 over x. On the right hand side, you have just product of that log function. So important thing is that this UV are not remaining same. They are also playing some role. So UV is now going to VU. Okay, with when X is going to 1 over X. And what about the 3 term? So 3 term, you have this X plus 1, X over X plus 1, and then you have UV comma V, and then U comma UV. On the right hand side, you can see that you have the 2 F at 2, 1 and 1/2. This F at 2, 1 and 1/2 can be evaluated in terms of log and dilog. We have done in our paper, but I haven't written them here because they are pretty of them so that's why I have written in this form. But one can evaluate this function F in terms of known functions, log and dilog function. So when you see on the left hand side, you see that U and V are behaving a little bit weirdly, right? You have here UV, and then you have UV comma V, and then you have U comma UV, right? So actually, I will show you that they are not behaving weirdly. They actually is following a rule, and that rule is following. You take action of GL2R on this X comma UV. So how this matrix is acting on X, we are taking this fractional linear transformation that we all know. And then how that U and V are, that matrix, how is acting on U and V, that was the main point here. So how that is acting, so you are taking just U raised to the power A, and then V raised to the power B, and then U raised to the power C, and then V raised to the power D. And then you take F function on the both sides. So then you will have this form. So suppose, let's take an example of X plus 1. So when you have X plus 1, what will be the combination of U and V? So for X plus 1, what is the matrix? It is 1, 1, 0, 1, right? For X plus 1. So you take this matrix, if you take A equal to 1, B equal to 1, and C equal to 0, D equal to 1. This fractional linear transformation give you X plus 1, right? So what this gives you now? So U raised to the power A is 1. B is also 1. So you get UB. C is 0. So this U is gone. And V raised to the power 1. So you will have, with X plus 1, you should have UV comma V. And that is there, right? UV comma V. And when you take this also, it will also give you that combination of U comma UV. Because now matrix is 1, 1, 1, 0, 1, 1. So from there, you will get this expression by that action. So main idea behind this proof of this functional equation, first was to guess the ideal combination of F, because from the previous experience, we know that what should be the argument of X. We know that it should be X, X plus 1 and X over X plus 1. So main part was to find out how this U and V are behaving. That was the main part. And then later on, when we have this right hand side, then we realize that they are actually behaving like in this with this respective to this action. And the same thing is with the 2 term. We have 6-term functional equation also in our paper that I have not mentioned here. That 6-term functional equation does also actually follow this rule that I just mentioned. Okay, so what is the main idea? Main idea that I just mentioned, that was to find out this action and the ideal combination of these functions on the left hand side. Then, and what is the definition? This is the definition, and then you just do the change of variable in this F, and then you get this one. So by looking at the definition of F, one cannot see the symmetry, right? In functional equation, what do we have? We have symmetry with X and 1 over X, right? So with F itself, you cannot see the symmetry. The idea is that you take the derivative with respect to X. Then what you see, you just started to see the symmetry between this U and V and this X and 1 over X. So the idea behind this proof is you work with F prime. You kind of find out functional equation for the derivative of this function F. And then later on, you just integrate it and find out that integrating constants and all. So the main idea is only this. You just find out the ideal combination on the left hand side, and then you work with the derivative of F, not F itself. You have to work with derivative of F so that you have that symmetry coming up very easily from the derivative. So I will not go into the details. So now I will discuss the special cases of our functional equation. So let me go to that slide. As I have mentioned that when you take u equal to -1 and v equal to -1, this script f function actually reduces to g of x. So if you take u equal to -1, v equal to -1 here, so what you get? This is g of x and this is g of 1 over x. Because -1 doesn't make any difference because u and v are same. So you get a very elegant functional equation for g of x, which is g of x plus g over 1 over x is log square 2. This function was actually extensively studied by Zagier, Radchenko, Muzaffar, and many mathematicians starting from Herglotz. But this functional equation somehow they missed. I don't know why. Like they have not, anyone hasn't mentioned in their paper. So it is actually coming a very easy consequence of our functional equation. So then one may think that whatever the three-term functional equation for J, first we thought that it may come from here by specializing of u and v. So when you specialize u equal to -1, v equal to -1, here you get g of x because f of x -1 is j, right? But when you take here in this, so this middle argument becomes 1 when you take u equal to -1, v equal to -1. That means this middle function that it is not j now. It is some different function. So you cannot get three-term functional equation for j from our functional equation directly. So then we have to find out other methods so that we can find a three-term functional equation for j. But we got success partially, I would say. So I will say why I say so. On the left hand side, you have that three-term 3j at x -1 and x over x -1. But on the right hand side, ideal thing will be getting some new well-known functions, elementary functions on the right hand side. But we cannot remove this script f function at 1 -1 and 1 -1. They remains there. So it will be like a good idea if one can find a three-term functional equation on where you have on the right hand side, you just have some elementary functions, some combination of maybe dialogue or log. So this is the three-term. So whatever the t of x, because we know that there is a relation between script f function and that t function, which has arctan function in its integrand. So by using this relation that I mentioned between t and f, and by using the two-term functional equation for f, one can find this beautiful functional equation for t as well, where you on the right hand side you just have pi square upon 16. Okay, so this was also not known in the literature. Okay, so
Rahul, can you go back and show us once again? Yeah, here. So f of 1, -1, yeah, right? Isn't it like connected with j?
But because it will not connect it with j because of this u. So let me show you the definition. Because when you take u equal to 1,
okay,
you don't have plus sign.
Yeah. Okay.
J you should have plus sign between u1 and so
that
is a different function. Yeah.
Okay, I see.
Yeah. Okay. So same thing is here because this is also 1 and -1. Yeah. Okay, so this is the two-term functional equation. So now let me go to the special values of these functions that appear that we have discussed up to now. So there we will see the applications of these functional equations for j, t, and all. Okay. So Herglotz, first of all, and then Muzaffar and Williams, Radchenko and Zagier evaluated jx at various special values. So this is the example from the Herglotz paper. He evaluated at various quadratic units. So g of 4 plus root 15 can be given in this simple terms, in terms of log. And Radchenko and Zagier provided some of the evaluations here. So they actually have two big tables in their paper for the special values of J. So I will discuss how they got these two tables as a special for the special values of J. And Muzaffar and Williams also evaluated this J as well as T. They also evaluated T. And important thing is that when you look at their proofs, these evaluations are not coming very straightforwardly. They are coming from the using Kronecker limit formulas. So it is not easy to evaluate this integral at 3 plus root 8 or any other point, like any other quadratic unit or rational numbers. So from here, you know this g of t, right? And from the functional equation, once you know g of x, from the functional equation, you would know g of 1 over x. What is g of 1 over x, right? Because on the right-hand side, you doesn't have any function or anything. It's just constant. So for an example, we know g of 3 plus root 8. What will be g of 1 upon 3 plus root 8? So you can write 1 upon 3 plus root 8 as 3 minus root 8 by multiplying and right. So what will be g of 3 minus root 8 by using the two-term functional equation? It looks like this by using the evaluation of this. So by an easy consequence of these two-term functional equation, now whatever values is known in the literature for special values of j and t, now you know those special values at 1 over x also. That may be difficult by direct evaluations because it contains non-trivial application, non-trivial techniques. So this is one of the application of these functional equation. Okay, so now let me discuss how Radchenko and Zagier obtained their two tables in their paper. So they define this script j function in terms of that j function. They actually add and subtract these two terms. And by using our two-term functional equation, one can have this functional equation for this script j function also. They have not mentioned in their paper because they didn't realize that j function has a functional equation as well. So, but it can be find out that g of x plus j of 1 over x is equal to 0. And they evaluated then j of x. Once you know j of x, then you can know j of x also, because these are the just constant terms, right? And this is their theorem. What they prove is that the values of this script j function is a linear combination of zeta 2, log 2, log n plus root square n square plus minus 1, and the value is rho of a. And what is rho of a? This is the Kronecker limit formula. So you can see how is Kronecker limit formula coming into the picture when you are trying to evaluate one definite integral only. G of x is a definite integral. So that's why it is very non-trivial, and this proof has like it's a proof. It is very non-trivial proof. So, but from once you have this theorem and you have this functional equation, then you can evaluate g of 1 over x also. So as an easy consequence of this functional equation, our functional equation, one can say not only these values of j, but these values of j will also be a linear combination of same values, because g of x is equal to g of minus 1 over x. So that those two tables of special values now can be given for g of 1 over x as well. Okay, so this is the special values of j obtained by Radchenko and Zagier, and then a easy corollary of functional equation, and their result is the following corollary that we provided in our paper. So then we actually realized that j is also not known for natural numbers in the literature. No one actually mentioned that what is the evaluation of j at natural numbers. So we did that in our paper and find out that j of n can be given in this form, where you have this Li2 coming up. Li2 function is a well-known function. It is well studied. So you can say that it is actually can be evaluated in terms of Li2 function. And by using the functional equation, then immediately you can have g of 1 over n also. So, but then we like try to, if we can remove this Li2 also, it is always like a good thing to have elementary functions only. So then we did some calculation and find out that one can do that for even natural numbers only. Not, we don't know that for odd it can be done or not, but for even natural numbers, j of 2m, that Li2 function, that whole sum now can be reduces to log of sine and log of cosine. They are like more elementary function in comparison to Li2. So this is the result for g of 2m. And again, g of 1 of 2m is just an easy consequence of that functional equation. And what about t at natural numbers? That can also be given from that relation between t and f. So this is the evaluation of t at natural numbers. So now you have this 4 Li2 function. So argument of Li2 function may look like complicated, but once you have this n fixed number like 4 or anything, then these actually nothing but 1 minus I or 1 plus I. So it is not a complicated argument. Okay, and then again, by using that functional equation, one can have this evaluation of T of 1 over N as well. So how we are getting these special values? These special values are coming from our one general theorem that we obtained for that Herglotz-Zagier-Novikov function at rational numbers at P over Q. So there you have this these finite sums, and you have this Li2 minus Li2. So by specializing this general theorem, we can find special values for J and T at natural numbers, and as well as for rational numbers as well, that I have not mentioned, but that can be done by using this theorem. Not only that, this theorem actually gives you many integral evaluations like the following. You have this integral 0 to 1 log 1 minus T raised to power 1 over N 2 minus T. I checked some of the tables of integrals. So this was not actually it is not mentioned anywhere. And it can be evaluated in terms of these elementary functions like log and all. So you can find many such special values of these kind of integrals from this general theorem. Okay, so why we are like one interest in special values is due to the following reason. So this is the Kronecker limit formula derived by Novikov. Here you have this that 1 over S minus 1 term, which gives you residue and pole. And this A epsilon function is a little bit complicated. It depends on that fundamental unit of real quadratic field. I have not mentioned that function because it's not it is not interesting to our discussion today. What is interesting is this Kronecker limit formula contains this combination of f at epsilon and at 1 over epsilon. So what is this epsilon? Epsilon is quadratic unit. So if we want to use this two-term functional equation, we should have uv comma vu. That is not there because here you have exponential 2 pi I mu over c, and here you have exponential 2 pi I a mu over c. And here again, like here u and v are like same, uv, then again you have uv. But when you take a equal to 1, they become same, right? So then you can use this two-term functional equation, and then you will have then only one f. And then up to now, we don't have special values of f at quadratic units. If you have like if one can find like a nice formula for f at quadratic units, then this Kronecker limit formula of Novikov will be reducing to a nice closed form expression, and then you can find a better formula for class number and all. So that applications of Kronecker limit formula, then one can explore that. It has some like finding some fundamental unit of real quadratic field, like that is nothing but the solution to Pell's equation and all. So this is the one reason one may be interested in special values of epsilon, that script f function. So that is what I just mentioned. And so today we just discussed what are the like functions that appear in these kind of Kronecker limit formulas. We didn't like discuss any new Kronecker limit formula today. So in this paper, we actually didn't obtain a new Kronecker limit formula. We just studied these functions that appear in these Kronecker limit formulas. But in the upcoming paper, that is, we are going to submit maybe, I don't know, in a week or two. And there we actually find a Kronecker limit formula for real quadratic field that was not known. It was known for imaginary quadratic fields, but real quadratic field case is always difficult. That as I like mentioned, that for imaginary quadratic field, Kronecker did it, but for real quadratic field, Hecker did it, and then Zagier, because it contains that infinite order of units. So it is a difficult case, and now we have obtained a higher Kronecker limit formula for real quadratic field up to now. And in that Kronecker limit formula, what we are actually getting a higher version of this Herglotz-Zagier-Novikov function that we discussed today. And so that and then as an application of theory of this higher version of f, which is like using its functional equation and using this Kronecker limit formula, we evaluated zeta values at higher natural numbers in this paper. So I hope that it will be gone soon for a publication. So this is all that I wanted to say today. Thank you, and please let me know if you have any questions.
Thank you, Rahul, for a beautiful talk. Any questions?
So yes, Rahul, hi. Can you hear me?
Yeah. Sure.
Thank you for wonderful talk. Okay. So I was just wondering that, like I was like writing a few questions when you were presenting that whether this Herglotz function at natural number can be evaluated. And
yeah,
that
can be done from that I mentioned a general theorem.
You have
you can take just q equal to 1 and p equal to n.
Yeah, j of n. I was interested in j of n, and you have mentioned already, like j of n and j of 2n.
So in fact, I have a question related to yours, Vivek. So you had said about j of 2m being in elementary. So I was wondering if there is a Ramanujan type formula for j2m plus 1. Because it's very parallel to how it is for zeta 2m and zeta 2m plus 1. Zeta 2m has an explicit evaluation. So j of 2m plus 1 may have a modular relation. I mean, it comes in some formula where you have a modular relation.
But
that's what happening. Like j of 2m is able to he is able to evaluate it.
Yes.
But j of 2m plus 1 is becoming complicated, like maybe difficult.
But for this script f function that in our papers with Rajat, that we have analog of zeta 2m plus 1 for higher Herglotz function, that they get psi plus psi and psi plus psi. That I had, that I have like obtained.
Okay.
But that is for different project. But right now,
But for her, for some general
for script f function.
Okay.
That I like to. So from there, one can get for j as well. But for Ramanujan formula, that I don't know. Maybe.
So j2m plus 1, as in not an explicit evaluation, but it might come as a residual term in the Ramanujan type version.
Yes. It may give some information at least.
What would be the analog of Eisenstein series in that case? Is a
that's a different question.
And like Zagier, like you mentioned one result of Zagier. So where he evaluated at n plus minus square root of n square plus minus 1. In terms of, he has written in terms of this is the rational linear combination. Does he says anything about here? I can see that these are all like, if we multiply with conjugates, then it will be either plus 1 or square root of minus 1. Okay.
That's why quadratic. They have this quadratic units.
Quadratic units they are considering. Okay. So my question is that whether he has mentioned anything about like transcendentality or algebraic nature of these values?
No. It would be a good. It is a good
any values till now, whether do we know any values of j of 1, for example? Okay, whether it is algebraic or transcendental, can you say that?
So you can see from like here, so j of 4 plus root 15.
Okay.
So then it contains a log and like, right?
But
it's a valid question. So I don't know.
I don't know. Actually, there is a result like pi and log n, whether they have been linearly independent over Q or something like. I'll see. Okay. So we do not know much about the algebraic or transcendental nature.
No, we don't know anything up to now.
Log n it is known as, except n equals to 1, they are known as transcendental, I think so. Okay.
So the idea would be get a Lorentz type formula at least for it, m plus 1, which will allow us to say at least one of them is transcendental.
That will come from, as you suggested, from Ramanuj's formula.
Yeah, if there is.
Actually, I have one question. Like, this is Muka.
Sure. Hi.
Yeah, sure, Sumita, yeah.
So they're like you told about like how that action of that upper half plane, that x uv, right?
Yeah. Let me
Hello,
go
can
to
you hear
the.
me?
Yeah. Here, right? You are talking about this action, right?
Yes, right.
Yeah.
So like actually the first one is that like first modular action on x,
Mhm.
right? And actually that u like action on u and v, is it related to any of that like kind of which we have already seen kind of action, that the action on u v is this kind of action come up in anywhere, like maybe in some kind of modular form or anything of that kind?
Yeah, that is a good question. Actually, we discussed it for like a month or two with Professor Choi when I was in Korea. So we were trying to see it. On the first place, we thought it is related to Jacobi forms. So, but yeah, up to now we don't know like it is related to any modular form or not. But we explored this this type. Yeah. But yeah, we don't. It is.
It will be interesting actually, whatever you are getting the relation, like particular case of matrix like ABCD or particular, like if one can evaluate some general formula with any ABCD.
That is what actually Zagier and Radchenko do in their paper using that Hecke operators theory. They find one general formula for any ABCD, and from there they get like hundreds of functional equation actually you can get from there. Then so you have a general formula, and then you just just substitute ABCD which are coming from SL to G.
Okay, so they have for that function, particular function and general formula they have given.
They have given for Herglotz function. So
okay.
that is another question that can we do the parallel thing with the Radchenko and Zagier.
Yeah.
Sumukha, you have worked in your PhD thesis on modular form generalization. Where you have three variables, right?
Yeah, right.
Then you can look at it.
Yeah, but it was not like this easy. Kind of the second relation was not easy there. Like it was not here. It is like just like u power a into v power b and u power c into v power d, right?
Yeah. So that might make it difficult to get back into F, right? That's what you're saying.
Yeah, exactly. There it was like it was like some semi-direct product was there already on that group, and it was like second and third variable action was like little more complicated. Like if you say Jacobi form action and all, or like even in her like of that kind of Hermitian Jacobi or anything, that's like the like second and third variable action.
So because like you